Sharing the screen. I hope everybody is able to see my screen. Is everybody able to see my screen?
Yes, Shadin.
Oh, thanks for the confirmation. So yeah, welcome all and thanks for joining in. Thank you for giving me this opportunity of presenting the latest topic, the latest trend in that machine learning and deep learning world, which is distributed training. So today we will exactly see how PyTorch distributed training helps in converging our model much faster, while also maintaining the accuracy and also giving high throughputs. So yeah, so the agenda for today is basically that how to train models 20x faster, obviously, given that we have the resources with us using PyTorch DDP. Okay, yeah, let me go ahead. So what we will today talk about, right? So in today's presentation, we will talk about what exactly is distributed training, and we will touch upon how exactly PyTorch has the DDP module, which enables us to do distributed training across not just in across GPUs, but also across different servers having different GPUs, right? And we will also touch upon how DDP works, how exactly the distributed data parallel like makes faster training, right? And then we will also see practical hands-on example of how the single GPU training works and how which single GPU training which we all are aware of, and multi-GPU training, how exactly it is done. And also we will see how multi-node GPU training is done. When I say multi-node, it is basically like consisting of two or more servers which has GPUs, and how we can have one parent server which can connect and synchronize with all of the other servers to do the training, right? And then we will also touch upon the torch run module, which enables us to quickly do this multi-GPU or multi-node GPU training. With this module is provided by Torch itself, an inherent module which basically provides this functionality, right? And also then we will also see a live example of how we can use this multi-node GPU training for getting the model to be trained faster for a GPT-2 example, right? Okay. And by the way, guys, if you have any questions, please park them in the chat section. We can definitely talk about that. And yeah, if you have any major questions, you can definitely ask it right away. Okay. Yeah, let's talk to the let's basically address the elephant in the room. What exactly is distributed training? So distributed training is nothing but it is nothing but a technique which involves training using multiple GPUs, not just like using one single GPU. Have you had you might, I mean, we all might have experienced this, that our model size is pretty larger, or the batch size which we want to use for model training is not it is not able to fit into the GPU with the limited GPU memory we have, and we often get OM error, like out of memory error, or sometimes the model file itself is so large that you cannot basically import it into your GPU, and it basically results, even if it fits, then it results into a very slow convergence time, right? So this is where GPU distributed training comes into picture. Like distributed training is basically a technique that not involves like training the neural network across multiple GPUs, and it basically allows not just faster training times but also like better performance, because better generalization, because we will see how exactly that is done. And how does it help? Yeah, like using multiple GPUs is especially important, especially at the invent of we right now we are talking about, we have progressed to such a space that we are right now talking about 13 billion model files, like 13 billion parameters for models, 40 billion parameters. So we definitely, even how powerful the GPU it is, we definitely can't fit that entire model into one single GPU. We, for fine tuning it or even for doing inference, we definitely need multiple GPUs, and that is how distributed training helps. Okay. So yeah, as we were saying, right, what exactly are the challenges using single GPU? right? I mean, the first, obviously, the major obvious challenge is that having limited processing power. Like single GPUs only have limited computational capacity, and even though if we can fit the model, there is a longer training times, and also like more the complex the model, the more it takes more time, right? Memory constraints, obviously, if the batch size or the size of the model exceeds the memory which you have in place, then definitely you won't be able to do any inference. And third thing is the reduced scalability. Obviously, we can't scale our model training to just rather than just having one machine. We can't scale it. If we want to fine tune a model like GPT-2 or even a LLM, or even let's say something which has a huge data. For example, in our real example, what we have done is like guns data it had basically for the guns model, we had not just the text but also the image model as well, which wasn't fitting into single GPU. So we had to use DDP, like distributed data parallel, for processing that. Okay. So yeah. Okay. So how does DDP overcome all of the challenges which is faced at like using single GPU? So the first thing is accelerated training speed. That is, you can, if fine-tuned properly, you can have at the minimum 4x speed, and at the max, like it depends on the hardware, you can have more than 20x speed in the training phase. Like if by introducing multiple machines and multiple GPUs for training, you basically are reducing the step size which is required for the optimizer to update the gradients, right? So by splitting data across multiple GPUs, training time also gets reduced, and also you are basically making the model to converge much faster. And the second advantage, or second, which is a good thing about the distributed data parallel, is that you can use larger batch sizes. Since like multiple models are processing the batch sizes, right? Like multiple GPUs are processing the models, you can distribute each of the data, like one portion of the data distributed among the other GPUs, so that suppose if you are able to fit only, let's say, batch size of 16, right? You can actually make it to 16, like, and suppose if you are using 4 GPUs, so 16 into 4, that is 64, you can make the batch size. Like that basically enables you to use large batch size, and again, leading to much better optimization and also faster convergence, right? And third thing is obviously the scalability and resource utilization. You are utilizing like the extent of which the models can get, and also the GPU memory which you can get, and you are scaling it up in such a manner that you are utilizing every ounce of computing power which you have, right? So Torch Run basically automatically does this for you, but we will see how to do it practically, I mean, manually as well. Okay. So yeah, moving forward. So I will just give you a brief understanding. This is a very basic understanding of how single GPU training works. Okay, you guys might all be aware, but just to touch up all the points so that everyone is on the same page. So let me quickly just play this video. So what typically happens is you have a data loader, and this data loader, basically from this data you get an input batch. This input batch is forwarded to the model, and once the input batch is forwarded to the model, right, the model propagates forward and does also backward propagation by calculating the loss. This loss is then taken by the optimizer to update the gradients. And this is the story behind how a single epoch for a single with the help of a single GPU works, right? This we all might have done in PyTorch or TensorFlow. This is a common story for each and every one, that there is a data loader, and it basically on every iteration it basically provides you the data for each epoch, and then it basically does the forward propagation, calculates the loss, then does the backward propagation, updates the optimizer steps and all, right? So this is the story of single GPU training, right? Yeah, just a minute. Yeah. Yeah. So coming on to how exactly multi-GPU works. Okay. Yeah, just a minute. Yeah. So multiple GPU, in this case, you have not just one GPU, but multiple GPUs. And in the multiple GPUs, the model files are copied. Okay, so when I say model files are copied, basically each GPU have the same exact model with the same optimizer state. So whatever model file you will be loading, it will get copied to each of the GPUs. It will be a replica of each other. Okay, and then what happens is that all these whenever you start the training process, okay, whenever you start the training process, what happens is this model will run separately. Okay, this will basically run separately by taking some random input sizes. So sorry, some random data points from your data loader, and it will run separately. It will act as its one. How exactly, if it will be for a single individual model, it will just run exactly the same, but there will be a synchronization process which will update, okay, the parent process or the parent module, that okay, what are the gradients for all the rest of the modules. So yeah, let me just, so as of now, just what the exact which you need to understand is that all of the GPUs will have a replica of the same exact model with the same optimizer state. Okay. Yeah. So how exactly this data gets distributed, how exactly the model gets the data, the random data, and how exactly we lead to a faster convergence is will be explained in this video. So what typically happens is that you have, instead of a data loader, you have a distributed sampler. Now the role of this distributed sampler is to the role of the distributed sampler is to provide randomized data to each of the model files. Okay, and each of, since we are providing randomized, I mean for that specific one epoch, since we are providing different data points to each of the model, every other model will have its own gradients, because obviously what typically happens is that if you give the same model with the same optimizer state with different set of data, it will obviously converge and have the gradients differently, right? But how exactly does it work? Right, it will do the forward propagation, and the backward propagation will do the optimizer update as well, right? Yeah, it is like, yeah. And once it is done, okay, once it is done, then what it will do, it will synchronize within itself. So if you see, like what it will do is it will now synchronize within itself, that okay, this is the model I have, I mean model one, on the GPU 0 will basically say these are the gradients which I have, and GPU 1 model again will basically say this is the gradients which I have. It will basically synchronize with each other, and at the end of the epoch, what it will do, it will aggregate all of these gradients into one, and will try to basically, like the basic example would be that it will try to aggregate, let's suppose calculate the mean of the gradients, and after calculating the mean of the gradients, it will basically at the end of each epoch, every other GPU will have the same model, because every other GPU will have the same mean gradient. This is how you distribute the workload across multiple GPUs, by giving random samples. Although by giving random samples, but again, what is happening is at the end of the epoch, you are given with the mean aggregated gradient. So yeah. Any doubts, guys, until now?
Yeah, Shazir, I have one. So
Hmm.
basically, what you're saying is these are four different model files, basically, until the epoch is complete. And once the epoch is completed, all the gradients are then aggregated together or taken a mean. And that is when you're saying ki, you know, it becomes one model file, right? After
Exactly.
every epoch like that.
Yeah, yeah.
So, okay,
Hmm. So at the end of
okay.
the epoch, yeah, the model gradients will have the same exact gradients, and also at the end of the distributed training process, the same model file will be present across every other node. Okay, and you can like have any one of the model, because it is the same model itself. So at the start we have the same model. At the end also, you also have the like same model itself, but with the upgraded gradients.
Okay, I think, okay, I got it. But isn't it like training four different models altogether? Because you're basically using four different GPUs, four different machines.
Hmm.
And
Yeah, so that was my question. Are these four different machines or four GPUs attached to the same VM? Or
This
can it be
is,
both ways? This
it
should
can
be
be,
same VM, I assume.
yeah, it can be both ways, Anirban. So it can be also like you can also have multi GPU where you have the single machine which have four GPUs. But also it can also be a case where you are like you are training across servers, like each of the machines have multiple GPUs. Now all of those GPUs can be connected via a central master server, and each of the process will be initiated, and this same exact process will be converged.
Yeah, so does PyTorch support that directly, or do you need something like Ray or some other
No, no,
framework
no.
to make
PyTorch,
that happen? That supports directly.
yeah,
So it
PyTorch,
allows, so because some cluster setup has to be done,
yeah.
like, okay.
Yeah, so PyTorch supports directly. We will also see how exactly that is done as we go along,
Okay.
that how multi GPU is performed and how multi-node is also performed. The PyTorch has distributed a module within it, and also has torch run, which has all the capabilities. And also there are different backends available. The most prominent one being NCLL, NVIDIA Collective Community for Distributed Training. So that backend basically manages all the networks and the clusters and everything. We will see how exactly that is done. But this is the main idea of how distributed PyTorch training is happening. And at the end of the day, as I said, like once the model, each of the individual model converges, it basically performs the all reduce operation. When I say all reduce operation, it basically compares its gradients along with the other models, other GPUs which is present, and basically formulates a aggregated value of it such that every other model is the same at the end of the training pipeline.
Yeah, so there are four instances of the model, and they have to fit into each GPU RAM, and then they are working on different parts of the data. So
Yeah,
because the gradient descent, the gradients are calculated in batches.
yeah,
So yeah, it is of course possible that at the end of each epoch, they exchange either the gradients are combined for each of them, and then finally after the end of each epoch, all four will have the same copy of the weights, and then the next
exactly.
epoch will start. Yeah.
Yeah. And since we are now also distributing the data randomly, like every other model is not getting the same data. So this also makes sure that there is high level of generalization across the models. So you are not only covering, I mean, not only having the faster convergence, but also improvising the generalization. Yeah, I hope I can move forward. This was the main idea, but right now what we will see how
Somebody has a
exactly.
question. I think Abhinav has some.
Okay,
Yeah,
I'm so sorry, I'm
yeah,
talking
yeah,
with
Shadil.
you.
Yeah, yeah.
I think Nikhil
So,
also has some question.
yeah,
Yeah.
so Shadil, so while we are averaging that
Hmm.
after the backpropagation, the loss, all the losses, different losses there, and
Yes.
different weights are there. Okay.
Yeah.
So when we are averaging that, so does it really converge that faster? So suppose if I just see that curve, the loss curve. So if we
Hmm.
consider something the loss of the all four models. So when
Hmm.
we do DL by subtract by DL by DW, so the point will be somewhere similar for all the four models, right? And if we averages that, so it will be somewhere similar to that. So means how exactly it is converging faster. So I'm not able to
So
understand.
yeah, no issues. So understand this. Okay. I mean, yeah, I do. I mean, even I had this doubt when I started with this, but understand this. Suppose if you are having a single model on a single GPU, and you are able to now let's say use the batch size of 32. Okay. Now, what you want to do, you want to now, let's say, use distributed training so that you can do faster convergence. So when you use the distributed training, right, what typically happens, the same model will get loaded across multiple GPUs, but this time, instead of using batch size as 32, you can use batch size of 64. Sorry, 32 into 4 is how much? 128, right? You can use a batch size of 128. Now, by using the larger batch size, you are not only increasing the basically reducing the training time, but also distributing the data to different GPUs at the same exact moment, at the same exact point of time. So these models, they operation is doing in parallel. It is not in series. Like they don't wait for each other to get completed. They just synchronize so that I mean, obviously, since they start together, they just need still I mean a simple overhead time. But apart from that, since like you are just like you can consider that scaling. Like instead of like using us one pod, you are now using 4 pods which can handle multiple requests. Hope that answers the question.
Shadir, in continuation to this Abhinav's question, I also have one more question. If I have loaded 4 files independently into 4 GPU servers, or let's say, 4 GPUs, so won't the batch size remain the same? It won't be multiplied, right? It will still go out of memory if it goes beyond 32, because I have loaded 4 different model files in 4 different GPUs.
Yeah, so the batch size for it will remain the same. You're right, the batch size will remain the same. But since we are using now 4 GPUs, it will, I mean, you can say that you can have now at or combined, you can have more batch size. But what exactly reduces is the step size. Okay, what exactly, if you see, we will see in the real-time example, what exactly reduces the step size. The optimizer now doesn't, it will, for a single GPU, suppose if it requires 32 steps to converge, by using 4 GPUs, like it will 32 divided by 4, which is nothing but how much it is. 32 is 8, right? 8, yeah. So now, yeah, it will require only 8 steps per GPU for like basically propagating, optimizing it.
Okay, I think I still didn't get it, Shadir. I'm
No
sorry.
issues, no issues. Yeah, I mean, yeah, it is a little
Yeah.
difficult, but once
Yeah,
you go through the
actually,
code,
the
you will
only
see.
concern is I'm basically doing the basic linear match. If I have one file, I'm able to use 32 batch size. If I
Hmm.
have 2 files and I'm loading them separately also,
Hmm.
it's not that only one file is loaded across 4 GPUs. If that would be the
Yes.
case, like how normal distributed, when we're using this and then in PyTorch module, right?
Hmm.
Where you use one, and when you increase the batch size, you can see the usage in different GPUs.
Okay, so for answering your question, let actually, and also due to time constraints as well, let me actually quickly like show you guys one real example. Okay. So what typically happens that I will first go through the code, obviously, give me some time. So for demonstration purposes, this is like strictly for demonstration purposes. I have a train data set. Okay, this is again a torch data set as well. Now in the torch data set, I am basically having the data and having of the shape of 20 and the target as from 0 to 1, like this is like randomized, so that I mean I'm just plainly creating random data for running through the model. Okay, this is a data set, and the code for which the code basically which I have written for getting this example done is I have obviously imported all the libraries which are required. Now there is a trainer class. Okay, and then in the trainer class, it basically takes the model, it takes the train data, the optimizer, the GPU ID. Now there are, since like if you see here, I have 4 GPUs listed here in this machine. Okay, so now since I can provide any of the GPU IDs, and then save every is basically an option at how much, after how much epoch I should save the model. Okay, and there is a helper function like for running the batch, like it basically sets the optimizer to 0 CRAT, runs the model, gets the output, calculates the loss, does the backward propagation, and then steps like optimizer basically now like basically updates itself, right? And then also there is epoch, like for how much epoch you want to run. This is a helper function for running the epoch. It will also print with GPU ID how much, what is the epoch which is running, what is the batch size, and what are the steps required for converging of the model. Okay, like remember the steps here, it is very important. And also save checkpoint again for saving the checkpoint of the model. Okay, and then train. Okay, now yeah, train is nothing but like for simple train function. A low train objects is nothing but function which loads all of my data set and my model optimizer and everything. And yeah, actually, you know what, let me run this quickly because it will take some time. Python sample single GPU. I will run it for 10 epochs and save it at every 5th. So yeah, it will basically load up. Yeah, let me go back to the code again. So yeah, again, like I have a prepare data loader function which prepares the data loader, the data set, batch size, and like pin memory and everything, like the normal stuff which we do. And then we have a main function which collects each and everything together, puts it in place. The main function basically loads the training objects, prepares the data loader, gets the training class, and then trains the model. Right. So here the parser arguments, like we have total epochs and save every, and batch size, like here I'm using 32. Okay. And again, basically I'm giving device 0 because saying at CUDA 0. And yeah, I'm training the function here with using the main function. Okay. So if you could see here, it is now saying GPU 0 has been doing the epoch 0 batch size with the batch of 32, and the steps required for converging the model is 31,250. Okay. So I hope this is clear. Let us make it run until this. Okay. So these are the parameters, and it will converge after 10 epochs. Okay. Now, yeah, let it run. So until that time, what we can do is we can understand how exactly multi GPU works. Okay. So as I have shown the example that yeah, you basically need to the torch basically supports inherently all the things which is required for running this across multiple nodes or multiple GPUs as well. This is nothing but I have just made some changes with the same exact file to the sample multi GPU code. Okay, so here you have torch the same exact imports. And then here you are also importing the multiprocessing, which is responsible for doing the, I mean, spawning across the multiple processes within the same machine. Like here, we will spawn 4 different processes because we have 4 different GPUs, right? And then you have data distributed, from data distributed, we have distributed sampler. So the distributed sampler is the one, instead of data loader, we will be using distributed sampler because this is the one which is responsible for distributing random samples across to 4 GPUs. It will automatically take care of that. And then torch and in parallel, we have distributed data parallel. This is the module in which we need to wrap our model function, so our model object for utilizing the DDP. Okay. And then we also have from distributed, from torch.distributed, we have init process, initialization process function, and destroy process group as well. So whenever you are trying to initialize a function, you need to basically use these functions. Okay. So the first function, which is a little change in the DDP setup as compared to single GPU to multi GPU, is a function DDP setup. So we have to basically provide some configurations to the Python interpreter to make it recognizable for Torch to basically run it as a DDP process. So in this, I'm basically giving here master address and master port. This can be anything, like since you are running it on local machine. Okay. So yeah, master address is localhost and master port is this. And then here you also have to initialize a process with the backend NCCL. So NCCL is NVIDIA Community for Distributed Library. So and also we need to also like have a focus on these 2 variables, which is rank and world size. World size is nothing but you could say the number of GPUs available in your entire machine or whatever number of machines you're working with. That is nothing but your world size. Rank is basically what exactly it is a unique identifier for each processes. Okay. So like which process consists of which rank. Yeah, like as here's a unique identifier for each process, and world size is nothing but total number of processes, or you can say total number of GPUs, because ultimately total number of GPUs nothing but total number of processes you will run, right? So let's see whether it has converged. Okay, it is still yet will almost converge. Okay. So now, yeah, here again, everything will remain same. The only difference here is if you could see here that I have wrapped the model using DDP, the DDP which is coming from here. Okay, I have wrapped the model using DDP, and everything else will remain the same. And also here, I'm not directly putting the model to 0. Rather, I'm just like model to whatever GPU ID, like I will mention here while initializing that. It will basically go to 0, 1, 2, 3, or whatever it is, right? And then run batch will remain the same, run epoch will remain the same. Okay, save checkpoint and train also will remain the same. This load train or load train object will also remain the same. In the prepare data loader, the only thing which will change is shuffle will be equal to false, because we don't want to shuffle when distributing the data set. And also the sampler, we will also give the data loader the sampler which will be used for distributing the samples across multiple GPUs. So here you have to basically give the distributed sampler of the data set. Okay, so in the main function previously we didn't had anything like just loading up of everything, but in here you basically have to also set up the additional function DDP setup with the rank and world size, and rest everything will remain the same. Also additionally you will, like, once the main function exits, you just have to destroy the process group. Okay, so if you could see here, the Python sample single GPU 10.5 have taken 241 seconds with a batch size of 32 and a step of 31,250. Okay, and if you would see, everything remains the same. It is the batch size is 32. The data set also, sorry, the data also remains the same. Now, if I run the same exact example using multi GPU, what typically happens is, okay, Python sample multi GPU dot py 10 and 5. So what it will do, it will basically, now previously it was just using one GPU. Now if you see that every other GPU will be used, like as the once the data is loaded, it will get distributed to each of the GPUs. Okay, let it load. It will take some time for the data set creation. Yeah. If you see here, each of the GPUs now is occupied with the same exact model. Obviously, the gradients will be different, but after once that converges, it will like occupy each of the GPUs. Not just that, but also if you see the batch size, even though it is remaining same, okay, even though it is remaining same, it is the steps which is required for each of the model has been reduced by divided by 4, because each of the model, again, it is running on each individual GPU, right? And also you could see previously it was just GPU 0 which was doing all of this process. Now it is GPU 0, GPU 1, GPU 2, GPU 3, and this is for all of the epochs. Like if you just plainly divide 31 to 50 divide by 4, that is coming around 7812 something, which is nothing but the steps. So by doing this, like, you are not only just increasing the batch size, but also obviously by increasing the batch size and by introducing multiple GPUs, you are reducing the steps required for the model to converge. And by doing this, you are able to train your model much faster as opposed to single GPU. And yeah, and the rest of the code, and yeah, one important code here which I missed explaining is you have to get the world size. World size is nothing but toss.device count, which is nothing but the number of GPUs which you will have. And also you have to, using the multiprocessing library, you have to spawn multiple processes. Like in our case, we are spawning 4 processes, and we are using the mp.spawn main, and world size is the argument which was taken by the main function. Like the main function takes basically world size, save every. And here, world size, the n processes is nothing but the number of world size. The number of processes is nothing but the number of GPUs, right? So yeah, by doing this, you are able to now convert. See, now it basically took 241 seconds for with using a single GPU, right? But when using like multi GPU, you are able to do the exact same process, exact same thing with more better generalization within 112 seconds. Okay, that was quite, I was going on and on, but I hope you guys understood.
Yeah. So this was a good illustration. Shows what exactly. Yeah. So the compute is parallelized basically, and the joining of the gradients. Now that is the part which is a bit more elaborate, I think, how the gradients get combined. So, but that's anyway, distributed processing is all about that. So there will be an algorithm to merge them. So I think it will be probably one of the nodes will act as a central thing and do that and distribute. That's how it usually works. Huh?
Yeah, so typically node 0, which is GPU 0, acts as the master node, which is responsible for all the communication and all the synchronization, which is involved in it. You can also set the ranks. The rank 0 is basically responsible for all of this, and it basically gets all of the updates from other GPUs, all the gradients, not just the gradients, but also the other optimizer states and everything. So yeah, it is a collective process, like how a typical distributed system works.
Yeah, but the important thing is the model should fit into the memory of a single
definitely.
GPU.
Yeah, definitely. That is that. Like, yeah, you have to make sure that the model fits into each memory, whatever you are using, whatever GPU you are using. Tushar and Abhinav, I hope you guys got what you were asking for.
Yeah, Shadir. I mean, I actually understood it. So basically, are the weights of both these models same? This one which took 112 seconds and the other one which was trained faster. I mean, can we say that?
Are the weights?
I mean,
So
weights of these two models will they should be
yeah,
similar, right?
yeah, they
Very
are
similar.
similar. Yeah, they are very similar. We have checked. We have done this for we have real time. We have checked this, and both of them are very much similar. Now
Okay,
there will
okay,
be little deviation here and there, but not that a drastic difference.
got it, got it.
Okay, so this was just like using multi GPU. Okay, there are more examples like this. So yeah, we have seen like how exactly we can use multiple GPUs in one machine, right? And yeah, so but this again, this code is not fault tolerant. So when I say fault tolerant, what as in any distributed system, what exactly happens if one of the node fails, or if one of the node goes down due to any error, like it can be of any error. So the other node should be able to pick it up, or what it should happen, that all the nodes should drop down. And when you try to run this again, right? When you basically try to run this program again, it shouldn't start from zero. It should always pick it from where it has been left, right? For example, if you have already processed until epoch 5, okay, and now suppose if your model goes due to any error, it can be it can be a out of memory error, or it can be network error, it can be anything. So but if it fails, then what should typically happen, all the processes should go down, or we can set that up, and upon resuming the process, it should be able to pick from where it left, right? So that is what torch run enables us to do. So this multi-sample multi GPU isn't a good thing to have. So that is where sample multi torch run comes into picture. Okay, so what exactly is torch run? Torch run is again a library which is inherent to PyTorch. It basically gives you fault tolerance when running the models in a distributed system. Okay, and and also not just gives you not just makes fault tolerance, but also it makes it very easy for to run and combine multiple GPUs or multiple nodes and everything. We will see. We'll first see the code exactly. Okay. Yeah, but better I run it so that it doesn't take time. So I will demonstrate the same exact example using torch run. So I have the commands here. Yeah, let it run, and I will explain the code. So here, when I'm using torch run, okay, torch run, and here I'm say the flag standalone basically refers that it is a single machine in which I have all of the GPUs. The end process per node is equal to 4, or you can even say GPU as well. It will take whatever available GPU is there, and all the file at which the multi GPU torch run code is present. And this is again the number of epochs and the codes which we want, right? How much we want to save. Like suppose if I can also give 3. Okay, I will run it, and it will basically load up, and I will explain the torch run code. Nothing much here. The only thing which makes it easier is that in the torch, while if you're running it using torch run, then you don't need to explicitly give the master address or the master port. That will already be taken care by the torch run. You just have to initialize the process, and also give each process a local rank. Now there are two types of rank. I will first explain what local rank is. Local rank basically refers to in a single machine. Okay, in a yeah, in a single machine. Okay, in a single machine, suppose if machine 1 it has 4 GPUs, the local rank of this in a single, it will be 0, 1, 2, 3. Okay, and if there is a next machine, again the local rank for that specific machine will be 0, 1, 2, 3. Okay, this is nothing but naming the GPU processes. Okay, so this you have to set. And again, trainer will class will again take the model, train data optimizer, save every in snapshot. But here we are taking a snapshot. Now, what exactly is a snapshot? A snapshot basically is a snapshot of the model, not just the model, but also the optimizer state and also the epochs. Okay, so here we have the GPU ID. Again, we are assigning the local rank for each GPU ID. and save every is again like an epochs run. We will start at 0, and the snapshot path is the path at which the model should be stored. And if we are checking here that if the snapshot exists, then we will load the snapshot. What exactly is load snapshot doing here? The load snapshot is basically going to the location where your model file is already present. Okay. For example, in this case, it is already snapshot. So let me delete it, by the way. Yeah. So if it is already present, like if it doesn't exist here, then it will go with the normal process of training it from scratch. But if it already is present, then it will pick it up from there, and also will basically load the model file, and also understand how much epochs have already been run, and yeah, take it from there. Right. And similarly, we have a save snapshot function, which basically saves the snapshot, the model state, and the epochs run, and also the model file itself. Right. And run batch will remain the same. The run epoch will again remain the same. The train will remain the same. But here we are only storing the model on the GPU ID equal to 0. So wherever you have a parent process running, like we will only store, because if you are storing at or storing for every GPU ID, that then basically like you are storing for same versions of the model, which we don't exactly need. So yeah, that is why we are only saving the snapshot only like when the GPU ID is 0. Okay, load train objects will remain the same. Prepare loader again using distributed sampler itself, and the main function like in here you have to call the DDP setup, and everything will remain the same as explained. I have explained earlier, and here as well. Here the one major thing is like if you are using torch run, then you don't have to use the mp.spawn method, because torch run will automatically spawn those processes for you. It will automatically understand that how many GPUs are available, and it will process, and it will basically initialize that many processes for you, the main function. Okay, so yeah, so this is the code, and if you go to the terminal, you will see that yeah, it has, I mean, the snapshot has been saved. Why is it not going upside? Just a minute. Oh yeah, okay. So yeah, let us take an example. Okay, let us basically run it once again, like how fault tolerance occurs. I will like give a basic example. Suppose if I run this and I save it at 2. Okay, let it run. So this again like using torch run itself, as I said. It will run, and it will take some time for the data to load. Yeah, it has yeah, it has run for epoch 0, and it will save the model. You'll see that there will be a snapshot. It has saved the model at this thing. Let it run once again, and I will like I will interrupt the process at epoch 3. Yeah. Once again, if the model has been saved. So it has
Where
saved.
is it saving? It is saving on this
file
where you are starting the process, like
yeah,
on that file system. You can give other file systems, I'm assuming, but in this case, where is it saving? On your whichever machine you are running it from?
yeah, in the local machine, wherever I'm running it from here, the snapshot.pt. Now it has been stored. I have interrupted the process at epoch 3, right? And epoch 3. Now it should, if I run it again, once the data is loaded, it should pick it up from epoch 3. All the randomized state and the data distribution will be also kept. I mean, it will also resume as appropriately. It will say, see, loading snapshot.
It's basically sending, it's loading this and sending it to all the GPUs or the network. Yeah.
Yes. Yeah. So now if you see that the snapshot has resumed training from epoch 2 rather than epoch 0. So this is how fault tolerance can be incorporated in distributed setup as well. So this is yeah, so yeah, one of the good examples we can, like whenever we are trying to train a very large language model, or you could say any complex model, we definitely should deploy using this, keeping this in mind, right? And yeah, so let me quickly kill this process. Yeah, I hope everything is good until now. We have until now seen how we can see how you can use multi GPU and how you can also introduce fault tolerance and torch run. So one of the now major examples is how now this was only relative to only one single machine. Okay, that you have a single machine which has 4 GPUs, so you can like basically do all of this stuff. But what if that even single machine, like because you are limited to 4 GPUs, not even single machine is basically helping out on leading to faster convergence, and you need to use multiple machines. That's where multi-node GPU comes into picture. Okay, so yeah, so let me just. So this is again one more machine in which I have set up the entire. It needs some setup. If you see here also I have four different GPUs available, and here also I have 4 different GPUs available. I will first explain the code, what exactly goes in it. It is all everything is remaining the same. There is only few differences here. The first difference is we will be using something called as global rank as well. Okay, so I mean each individual process, although we are able to identify when we were using single machine, we were able to identify using local rank. But when it comes to using multiple machines, I mean, we then have to assign a global rank. Like when I say global rank, in this here, the machine one, machine two, right? The global rank for machine one, GPU one is will be 0, 2, 3, and again for global rank of the second machine will start from 4, 5, 6. So this is a difference between local rank and GPU rank, and this is essentially done so that each process can identify which rank of what is the rank of the machine, and they can identify their processes basically. Okay, so yeah, I just have to introduce this global rank. Okay, and yeah, and everything will else will remain the same. Like here, the loading of the snapshots, running the epoch, saving the snapshot and everything, training the data set, prepare data loader, main function, DDP setup, and everything. Right, everything will remain the same, and we will be also using torch run. But this time we will also use one more module from torch run, which basically enables the communication between multiple nodes. Okay, so I have this one notebook. Sorry, one instance. There are two instances, as I said, right? So what I need to do is I need to like just run this, run the same exact file. Okay, if I wait a minute, yeah, 0. Yeah, I have to run it here. So here in this, like torch run, n process per node, like each node consists of 4 GPUs. N nodes is equal to 2. Now this is a new flag where we are saying what are the total number of nodes which are available for this computation, which is nothing but 2. The node rank, like what is the rank of this node? Okay, like the node rank is 0, and node rank 0 is basically the master node, which basically is the owner of this entire process. And then there is also rendezvous ID. So this ID, rendezvous ID is basically used for identifying all of the processes which are running across multiple nodes. And rendezvous backend is C10D. C10D is nothing but a name for the backend which we will be using for performing this operation. And also you will also have to give a rendezvous endpoint through which the nodes will communicate to each other. So here I have given, like if you go to just a minute. Yeah, if you go to cat etc host, yeah, it took a while to figure me out how to exactly connect these two nodes. But yeah, so you basically have to use this internal IP address which Google provides for as the endpoint, and you can like check whether there is a communication between two endpoints or not. And if you yeah, just a minute. Yeah, and if you run this, now it would actually not just start the process, but instead it would wait for the other node also to spin up the same process. So here I will run the same exact command. The only difference being that the node rank, right? The node rank will become 1 here. Since the node we have assigned node 0 to the other server, here the node rank will be 1. And every other this thing will remain same. Okay.
So all of these will on all the nodes will start with that same rendezvous IP,
Yeah.
right? That
Yes, yes.
that endpoint, yeah. So that is actually the master sort of, yeah.
Yeah. So this is I have given the IP address of this machine as a master, so it will consider this as
Yeah.
So
On the
once you
other
do
one
this,
also it's same address, yeah.
Yeah.
Okay.
So once you do this, it will start. Now, if you see both of the, I mean, both of the GPUs will be okay. There is some error because I didn't delete the snapshot. Let me delete it. Uh, right. So yeah, this is like setting it up and it will run.
So
Okay.
the ID and that the ID, the IP address, these have to be
Yeah,
same
these
for all.
are crucial parts. Yeah. And also, like, you can also have machines where it is possible that you won't be having two, I mean, 4 GPUs. You can be having 2 GPUs only. So you can like specify that in in this n process per node equal to 2. Suppose if this machine has only 2 GPU, then it will only 2. And if you have like more than 2 nodes, then appropriately you can update. So see, everything is running, and you can see that your GPU 5, I mean the global rank GPU 5, say 7, 6 they are running, and also similarly like it is like GPU 0, 1, 2, which are responsible for this node is able to run, and we are able to like converge much faster here. So that is how you can basically like do multi-node GPU processing as well. Like suppose if we have some project where we require a huge amount of processing, and we need to distribute the data as well, and to have much generalization, better generalization, and also faster convergence, then it is better to, I mean, although we knew how to do this, but we never really tried because there was no necessity until now. Like with the guns and the cigarette model, the image classification model which we developed, we trained using single DDP only, single machine with 4 GPUs, DDP only, because it could handle that load. But if there comes a picture where the data is very huge, you can't fit it in one machine, then it is obviously very better to use this, right? Yeah, so this was like multi-node. And last but not the least, like I basically also to give a real example, what I did is I basically have studied this Andrew Karpathy's Min GPT. So it is here where they are training the GPT-2 with the same exact like DDP setup and get train objects, same exact process, how local rank and all that stuff. So if you want to run this across multiple GPUs as well, you can do the same. Just have to go to that specific folder on both of the nodes and have to same the exact same command. Right, it will load up. It will basically load up the entire thing. So by the way, this model is nothing but the trainer class. If you see, everything is remain almost the same. Everything whatever we have did is exactly the same. The global rank, local rank. It was a good data set. I mean, good GitHub to study, and also how to implement all of this stuff, right? And yeah, so it basically what it does is like, yeah, it fine tunes the GPT model with your own data set. Like and also here I'm using Omega config for having the config same across all of the parameters and the model files. So here I'm using this data for basically fine tuning the model. So there is nothing but conversations, and by using these conversations, like your GPT-2 can generate, I mean, get itself trained to generate the input output text, like here and layer and head and embeddings, trainer config, what is the batch size and everything, and snapshot and everything. Yeah. So yeah, and yeah, it has resulted into error because I didn't deleted the this thing. Yeah. So yeah, GPT snapshot. Yeah. So yeah, I suppose Yeah, I hope you guys understand what the difference between local rank and global rank, right? And yeah, so just following up with few tips when we guys are using for DDP, always remember that if you are using DDP across multiple nodes, then there is always a network overhead because of the synchronization process needs to happen, and especially if you are doing it within the machine, obviously there is no network lag. But if you do it across different machines, then there will be network lag, and that can result into failures. So it is always better to use 4 GPUs in a single machine to avoid network overhead and save cost, obviously, rather than having 4 machines having 1 GPU. Okay. And obviously, like just few tips is that consider cost incurred before starting the training. Always understand how much cost it will take and everything. And also before full-scale training, or test your model on DDP setup on a smaller subset of data to identify any potential issues early on, which helped a lot when we were doing the cigarette model. We identified there are a couple of issues which we fixed really soon, and then we basically used DDP to train the model. Yeah, that's it. I suppose. Thanks for joining in. But yeah, if you guys have any questions, then yeah, definitely. Yeah, yes, Willie.
Yeah, great presentation, Sadir. I have a question like, if we start with the 2 nodes and, for example, if one node's going down, what will happen with the training? Will it keep training or it stop? All of the nodes will stop.
So for that, right, you have an option. You can set up in both ways. So what would happen? I mean, I have set it up in such a way that suppose if one node or one GPU fails due to some error, the other node will go on processing the output. I mean, sorry, model training. It won't stop. Or else, if you want that, even if one node fails, then everything should go down. That is also possible.
Oh, okay, so we have the options to set it up. Yeah.
Yeah.
Okay.
Yeah, any other questions related? I will upload all of these code files so that you guys can go through it and obviously implement it whenever it is necessary to do the model convergence way faster in our Bitbucket. And yeah, obviously I'm open to helping if anyone has any doubts or issues related to this as well. But yeah, if you guys have any questions or anything.
Yeah, hi, Shalin. Thanks for the detailed this whole presentation. I think I missed some part. I was a little distracted. Basically, I had one question that if we have a very big model, let's say a 25 GB model, and we want to distribute the model just for, let's say, inferencing, not even for training, how do we do this across like multiple GPUs?
Yeah, so I mean here for the first question, there is actually here we are just doing DDP, which is distributed data parallel. We're distributing the data across different nodes. But there is something which is also called as FSDP, which basically shares I mean, instead of like suppose if you are not able to fit the entire model in one GPU. Okay, now what you can do is you can use multiple GPUs to share some components of model, like share some components of the model across multiple nodes, and the inference can be done. But if you are asking that how can we do inference using the setup which I have explained, yeah, you have an inference pipeline also available on Torch for doing that.
So for inference,
Okay.
the memory requirements are much less. So for the
Yeah.
training, it's a lot more. It's like, I think I had sent some, saying, I think it's 20 times more or something.
Yeah.
So yeah, and inference takes so much less resources. But yeah, the FSDP is again, from what I understand, is for training when is called fully sharded data parallel,
Yeah.
where the model can't be loaded into one GPU RAM. So pieces of the model have to be loaded separately. It's a
Yes.
more complex thing, and there's a lot more synchronization in that case. But inference-wise, the GPU RAM requirements are lower. So I think my feeling is for inference in that mode, like the ray that we use Rayserve. So the
Yeah.
Rayserve, right now we are using it only for batching. So that probably is the solution, like setting up the servers to be joined together in the Ray cluster.
Yeah.
My feeling is, I mean, I haven't gone into it in detail, but I think that's the way to go for inference with multiple GPUs.
Yeah, even if we require, like I have read multiple papers where they they need to do multiple GPU inferencing as well, and even for that, PyTorch has support for that as well. Like you can within one machine you can like spin up multiple GPUs and you can load up different models. Even for the, we actually have implemented that as well. What we did is for the, if you guys remember that during that Google ban cigarette detection, we had to run the entire data mart images through the model. Now, obviously, it wasn't possible for just to have one single process to do that, right? So we used the DDP or distributed inference for that to load up multiple GPUs.
Yeah, that's your batch inference. Yeah, when you do it through the jobs. Yeah. So
yeah.
The one that I was talking about is in case of service. Yeah, the two are different.
Yeah.
There you have to do it in the Kubernetes pods. So.
Yeah. Yeah, exactly. I mean, if you're able to fit that model in one GPU, then yeah.
Yeah, but probably this one is more likely to come for us, the batch job one, because until we come to the stage of hosting LLMs for inference.
Yeah. Yes.
Yeah, I think Ray probably can solve that also. We haven't used that capability yet. The thing is, again, like this cluster setup, there has to be some configuration where one is designated the master, and these, like, if that goes down, they elect a new master within that part. So, but we haven't probably tried it yet. But Racer for the service case, yeah, for this one you have already done, as you said.
Yeah.
Okay.
Yeah, I hope that answers the question, Nikhil.
Yeah, thanks, Adil.
Okay. Yeah. Any more questions related to any slide or anything? If not, then I guess we can wrap it up. And thankfully, we did it on time.
Yeah. Okay. Thanks, Shadi.
Yeah. Okay. Thank you, guys. Thank you for this opportunity.
Thank you, Shadir. Thank you, everyone.
Thank you, Sadir.
Thank you.
Thank you, everyone.
Thank you, Shadir.